All right, let's see if we can go ahead and finish up with problems 9 and 10. Hopefully that's not too long of a video set to find the things that people need. But here we go. This problem is actually structured, and part of the reason I put it on here is that it structures kind of like how a lot of teachers like to do that, and that's included in how an AP test would be structured. Where you start with a more basic question and you delve into some slightly more complex terms. So we have this graph of 16 minus x to the fourth and 12 minus 3x squared in the first quadrant sitting right here. Now, you can tell by context that this top one is 16 minus x to the fourth because its y-intercept is higher than this one whose y-intercept is 12. So that's fine. So we are going to be looking at this simple region right here. And we're going to first just try to find the area of that strange little shape that is right there. So again, that is no big deal. That's going to be the integral of the top curve minus the bottom one, right? So the top minus bottom, that's usually how we would do that. When I look at this, I would be looking at little Riemann sums going this way. So each of these things would be a dxy, wide, excuse me, I meant to say. So we're going to do that top curve, which is y2 minus the bottom curve. So I'm going to do the 16 minus x to the fourth on top. That's the far one. Minus 12 minus 3x squared, which is the bottom one. And that's again going to be going from 0 up until the place where they both bottom out here together, which of course is 2. Fairly easy to validate that 0 equals 16 minus x to the fourth. Take the fourth root of both sides and we get 2. That's no big. So we know that that's the value. A little bit of combination of like terms, 16 minus 12, of course, is 4. We've got a double negative on this x squared, but we still have a negative on the x to the fourth from 0 to 2. Not a terribly difficult problem to complete from this moment on, and I believe we get 48/5. And I don't think that's too bad of an issue. Sorry, I realized mine was a little bit below the screen. So hopefully that's not too bad of a problem. I didn't show you the power rule being done, but I think we can handle that at this moment. But now if we take that very same region, right, like this, and we chose to revolve that around the x-axis, remember we were going to have a pi r1 squared, but that radius from here to here is the y value, minus a pi r2 squared, where again, that radius would be from here to here, which is a different y value. So that's like a y2 squared, if you will. And so what I'm going to do is keep in mind, I want to know what is y squared, but this is going to be in looking just like we mentioned on that last piece, there's going to be a dx that's involved in that, which always happens. So we need to figure out what each one is. But we know already that the outer one is the outer y, and that y was 16 minus x to the fourth. But we don't just take y, we take y and square it. And then we're going to take the other y, which is 12 minus 3x squared, and we're also going to square it with a dx. Now, again, the process remains exactly the same as it has been. If you need to, we could do a little bit of math on it and say the 16 squared is 256 minus 32x to the fourth plus x to the 8. I already in a previous video kind of discussed how you would go about expanding this out and so that you can do your integral from 0 to 2. But if you can expand this out and expand this one right here out, I guess I might as well do it. That's 144. 12 times 3 is 36. So that'd be 72x squared plus 9x to the fourth dx. Now we can do all that stuff. A simple power rule is going to kick in when we work on all of this stuff. And you get a very simple 9,472 pi over 45. Seems like it'd be hard, but look at what a nice, easy answer. Now, this is something that they tend to do on AP tests is they'll give you something like this, and then they'll ask you something kind of weird like this, where it says, set it up, but let's not even bother to evaluate. Just can you make it kind of ready to go? So let's see if we can make this one ready to go. So we are going to take this same region we've been dealing with, here to here. We're going to lower down all the way down to y equals -8. So keep in mind, when we revolve this region from here all the way to this far one, again, it's outside minus inside, it's top minus bottom, just like it was earlier. Again, the far one minus the close one. Let's go back up to here. So it's going to be pi r1 squared minus pi r2 squared. So keep in mind, if from here to here is y, but from here to here is 8, because this region is 8 units below, it would be 8 plus that y squared. And then the other one is 8 plus the other y squared. Now keep in mind, this says set up, but don't evaluate. And just like the others, because our revolution is around something parallel to the x-axis, we would have these little wafers going this way. So it's going to be a dx. I really honestly set it up pretty well. I just need to now finish because I know that the x values, again, are going from 0 to 2. 8 plus that first y value is that outside piece, which is 16, trying to remember what it was, minus x to the 4th. That's 8 plus the y value is the radius squared. And then we have 8 plus the y value, which is, what was that, 12 minus 3x squared dx. Oh my goodness, we got to be careful. Now, this is a matter of preference, whether you chose to clean it up a little teeny bit. I think I want to. 8 plus 16 would be 24. 24 minus x to the 4th quantity squared, and over here it'd be 8 plus this, which is 20 minus 3x squared dx. And because it said, let's set up, but don't bother to evaluate, we've actually completed that story. We could do it. It's very, very similar to the previous one. It's just going to be bigger answers because we've expanded the radius a little bit. Okay, so that's it for problem number 9. And we just have one little problem to go, which is number 10. Okay, so in number 10, we have a similar setup, where they said, let's first off find some information regarding the area, right? So the first thing we're going to do is we are going to consider the square root of x, which is a nice simple curve that we've done quite a few times. And we are going to consider the line y equals 6 minus 2x, which has a y-intercept of 6 and a slope of -2. Well, that's interesting. So we've got this region right in here where there's a curve here, a line here, and a line here. Well, that's kind of an interesting story. Notice the nice curvature and the linear piece. So as we try to find the area, as we move along, it's really just the top curve. Oh, that's it. It's really just the integral from 0 up until, well, let's see, I guess we need to go all the way over here to where it crosses the x-axis would happen at 3, right? But what's strange is that right in this region, all of a sudden, I'm going to call this A, comma, f of A, there's a place where who's on top changes. So we're going to integrate the square root until I reach A, but then I'm going to switch from A up until 3, and then I'm going to end up integrating 6 minus 2x dx. So that is a little bit of an interesting play. So I need to find out when is 6 minus 2x equal to root x. So I guess I would square both sides. And we've been doing a little bit of this throughout the various videos. Keep in mind, if you take 6 minus 2x times an additional 6 minus 2x, this is what pops out. I'm going to, missed an x. Move that x across, and I would have 36 minus 25x plus 4x squared is 0. And that seems like it would be a really, really, really rough problem to find the answer to. But it turns out it is actually a factorable quadratic. It doesn't really look like it would be, but it turns out it factors pretty nicely to get that particular story. Let me think about how I factored that. To get a 4x squared, it's either a 2x and a 2x or a 4x and a 1x. And I'm lucky because I've done this problem in the past. Turns out 4x minus 9 and then x minus 4 will work. Those are the two values that actually come out of that. And so my first answer is if x equals 9/4. The other answer is that x equals 4. And I know that right there, when I look at those, I'm like, how the heck is x equals 4? It's not even there. But if you could continue this curve around down here, it's going to intersect out here at x equals 4. But we're not considering that portion of the curve because we just, it's and the x-axis. So my a value is 9/4. So we are going to integrate from 0 until 9/4 of x to the half dx plus the integral from 9/4 until 3 of 6 minus 2x dx. Not a super awesome set of numbers, but when I put it all together, I've got 45/16. Now, for the sake of brevity, I am going to basically point to another option. Instead of doing it the way that I did this, looking in this direction, I could have equivalently looked in this direction and set it up as an integral with a dy where the bars would be going this way. Now, at first you might be like, why would you do that? That seems like it would be harder, but the reality is the far curve is always the line and the near curve is always the square root. So it's actually a little bit easier problem if you look at it in that way. So from here to here is x2 minus x1, and I would be going from 0 up until f of a, whatever that value, that y value is, with a dy, because we're looking at it in that other way. So keep in mind, if I did do that, I could resolve this thing right here. See this equation, I could solve it for x, and x would be y take away 6 divided by -2, which is -y over 2 plus 3. This one, if I solved it for x, I would get y squared. And we're going to integrate that from 0 up until what happens when you plug in 9/4. But 9/4 square rooted is 3/2. And if you take a minute to go through this process, you're going to get exactly the same answer. And I have done that. And I actually think that was an easier solution than this one over here, because I didn't have to set up two integrals. But let's see what we can do. We are now going to attempt to revolve this crazy shape about the y-axis. And part of the reason I wanted to look at it through this red set of values is because that's really what it takes to do this problem and revolve it around the y-axis. Because you, yet again, are going to integrate the far curve. So from here to here is x, pi x squared minus pi x2 squared dy, because again, the washers are going in this direction. Hopefully you can understand that little picture. We've got this outer x and this inner x right here. But this outer x from here to here, we just solved for that a second ago. It was 3 minus y over 2 squared. This inner x was just y squared. And our y values, we already established, went from 0 to 3/2. And sometimes you get lucky and you've done some work and you get that answer reasonably quickly. Not a very pretty answer, but 711 pi over 80 is what I got. And then the last two ask us simply to set them up, but don't bother to evaluate. And it's not that you can't evaluate it, but obviously if you've done a few, you could do the others. So this time what we're doing is we're going to take this curve. Again, this is our story, and I'm trying to exaggerate like the curve and the line. And we're going to revolve it around some line out here at x equals 7. So the part that's tricky about that, let me go ahead and shade this in so it's very clear the portion that I'm talking about. From here to here is the radius. That's pi r1 squared minus pi r2 squared, as it always is every single time. But the distance all the way across is 7. This distance is x. So it's like a 7 minus some kind of an x squared. And we're going to subtract some 7 times some other x squared. And again, because we're revolving around, it's actually revolving this way, but it's parallel to that axis. It's going to be sitting out here somewhere. You're revolving around something parallel to the y-axis, so it's going to have a dy. So the only thing we have to do is make this agree with this letter. So what we know is this outer x, if you look right here, this outer x, if I solved it, x would be y squared. So there we go. So 7 minus x, 7 is minus, excuse me, I just said y squared, didn't I? Getting tired, I've been doing too many of these. And then the inner one, that x value we just discussed a few moments ago was 3 minus y over 2. And then squared with a dy, and those y's went from 0 up until 3/2. So the setup, again, is that pretty? Absolutely not. Could we clean it up a little bit, like 7 minus 3 is 4? Sure. But it's really pretty gross, and it's just going to stay that way. And then our very last problem is if we were to take the region, it became less pretty as we went here. We're going to take this region right here, and we're going to revolve it around this bottom line, y equals -2. Now, unlike the problem that I talked to you about before, this one, I don't know of any way to do it. Well, never mind. I do have another way to do that, but we haven't learned how to do that. There's a version called cylindrical shells that we'll probably address after the AP test. But as you revolve these discs around this and we slide it across, what's going to happen is the limiting function is going to change from the square root function to the linear function. So when I do that, I still have a pi r1 squared minus a pi r2 squared, just like we've been doing all the way along. The thickness is going to be a dx. But in this case, instead of making it less of a radius, I had to go 2 units plus y. 2 units plus y, because from here to here is 2, from here to here is y. And I don't know why I did that, but I'm going to do a plus because we have 2 separate regions. One of them is going from here to 9/4, and this one is going from 9/4 up until the last value, which I believe we said was 3, because we have 2 separate regions that we have to deal with. So my setup goes from 0 to 9/4, then 9/4 to 3. They're both going to be dx's. But instead of going 2 plus y1 squared, we're going to go 2 plus the square root of x squared. And over here, we're going to go 2. Let me see what I did on this one. Plus 2 plus the other y value, which was 6 minus 2x squared. And I have set that up. I have chosen not to evaluate it, but my understanding is I believe I have set that up correctly. I'm looking back at my notes and I have something a little bit differently written there, but and I now know why I have something different because I forgot something. I found the volume if I had taken all of this thing all the way down into here and revolved it, but I actually want to remove this central portion right in here. So I need to take away the integral of pi r squared dx, again, from 0 up until 3, because all the way from here to here, from 0 to 3, my limiting factor is just a radius of 2. I almost missed it, but I figured it out before I left it. So that's the end of the review. That last problem is a little tricky. I'll see you back in class. Hopefully that was helpful. Talk to you later. Bye-bye.